Hi guys, Alex here at Network A1A and welcome to a brand new video. This is part 3 of the episode 1 of the CCNA Labs series. So I'll split it up into 3 parts, as one big video would just be too big to put out there and you won't really want to watch and sit through it. So in this video we're going to be implementing Ospf. So in the last video we had HSRP, the video befer that was the router 1, router 2 and router 3 1, and the last video was HSRP, and the Birmingham LAN. So let's get into this video, which is Ospf. So we're going to be configuring Ospf area 0 over the tunnel, area 2 within the Birmingham LAN, and area 2 within the London LAN, and area 1 within the Birmingham LAN. So we're going to have multi-area Ospf instead of single area. So as you guys know, within multi-area Ospf, the other areas have to all connect to the backbone, so they have to traffic has to traverse the backbone in order to get from one area to the other. So that's why we have the area 2 hanging off area 0 and area 1 hanging off area 0. We couldn't be able to have area 2 and 1 hanging off, let's say, in area 3. So let's get right into it. So we're going to configure firstly Ospf over the tunnel. So we're going to try and get through this video really quick, as it could possibly be a very long one. Process ID of 1, this is individual to the router. It's not like an autonomous system number where they have to match with ERGRP. So we're going to give the router ID. So router ID of 3.3.3. This is just so we're able to easily see what routers we are confirming our relationships with. So you don't have to actually go into the router and see what IP address correlates to what router. We just know 3.3.3 is router 3, so it's nice, quick and easy. As you guys know, the election for the router ID, firstly, it goes off highest physical IP address. If there is a loopback, however, the highest loopback IP address will be chosen over the highest physical IP address, just due to stability reasons. So obviously a loopback will only go down if it's shut down manually, or if the router goes down, as it won't have any physical issues as compared to a physical interface, which will have physical issues somewhere down the line, possibly with a broken wire, broken interface, or broken port, something like that. And then obviously the router ID, actually specifying the specific router ID, that takes precedence over everything else. So that's what we've done there. And this is the I believe it's the 1.1, but I'll have to actually check that. So do show IP interface brief. So it is the 1.2. So it is the network 192.168.1.2 area 0. So we have specified this interface here, as we don't want to be sending our routes over the internet via this interface, so we're not going to specify this IP address. So we don't want to form relationships on this IP interface, and we don't want to send any routes out of this interface. So specify this IP address. This subnet mask actually just matches it specifically, so it's sort of like an inverse. This wildcard mask is like an inverse subnet mask. So it's like an all255 subnet mask where it matches a specific host. But if I wanted to match the host /24, I'll just do that, so that anything with a 192.168.1. whatever will then be advertised and be run on if we run on that interface. So like Ospf will be run on a 192.168.1.20 interface, for example. And obviously we've put it in the backbone, so it's area 0. So on router 2 we'll go comp2 router Ospf 1. We'll do the router ID of 2.2.2, and then we'll go in network 192.168.1.1, and then we'll do the wildcard mask to match it specifically, so the interfaces come up. So show IP protocols. As you guys can see, we have a router ID of 2.2.2. That's our process ID. We have these networks which you are routing for, so we have the specific 192.168.1.1, so that's the IP address that we are specifically running on. So whatever interface uses this IP address, it's going to run Ospf on that interface. A maximum paths of 4, so this is when you come to do your load balancing, equal cost load balancing. You can go across a maximum of 4 paths. And then we have our reference bandwidth of 100 megabit per second. This is the reference bandwidth which is used in the OSPF cost calculation. So the OSPF cost calculation is 100 divided by bandwidth in megabit per second to get your cost of that link. So this becomes a problem, say for example if we're using gigabit Ethernet links or 10 gig links which give you a decimal place. OSPF doesn't recognize decimal places, so it just rounds it up to 1. So a gig link will have the same cost as a fast Ethernet link, which obviously isn't good. So therefore, if we are using gig links, which is the highest supported link on the path to the destination, so if we're using a mix of gigabit Ethernet links and fast Ethernet links, we want to put the reference bandwidth as 1000 megabit per second, so that obviously it can specify the difference between the gig link and the fast Ethernet link, as the gig link will have a cost of 1 as 1000 divided by 1000 when changing reference bandwidth, and the fast Ethernet link will have a cost of 10, for example 1000 divided by 100, which will give you 10. So yeah, that's the reference bandwidth in short there. We're not going to mess around with that today because we're just going to be labbing, and the administrative distance is 110. So show IP protocols, or sorry, not show IP protocols, show IP Ospf interfaces. So we can see here that the interface, see our hello and dead timers. Broadcast links, hello is sent every 10 seconds, the dead timer is 4 times that. On a non-broadcast link, the hello timer or the hello is sent every 30 seconds and the dead timer is 4 times that, so 2 minutes. And you can see it's a point-to-point link, so in this case there's going to be no BDR or DR election as it's point-to-point, as it's going over a tunnel. And we can see our router ID and our process ID there. So say for example in an exam environment, if you can't see any other cores, for example they're in the same subnet, for this is in terms of forming relationships, they're in the same subnet, they have the same area ID, so they're in the same area, but they're still not forming relationships. Probably look at this and you will see that the hello and dead timers don't match between the two. It's not like EIGRP where hello and dead timers don't have to match. With OSPF they do have to match for you to actually form that relationship. So there's that. So we're going to also advertise we're also, what's going on? There we go. We're also going to advertise the other networks. So router Ospf1, and it's going to be our network 192.168.4.1, and this is actually going to be in area 1. So there's that done. And then on our router 6, which connects to router 2, we're going to go with our router ID of 6.6.6, and we're going to go with our network of 192.168.4.2. Put that in area 1 also, and I did put a loop back on this as well, which is 5.1. There we go, and we should see that come up in a second. So show up OSPF neighbor. Here we go. So we have a two-way connection, or a two-way state, so we know that we have connectivity to our neighbor. So we just obviously need to do the nitty-gritty things of exchanging database description packets so that we both sync our OSPF databases together. So yeah, we'll just wait for that to come up. It should come up any second, and then I will have a look at doing router 3, so advertising our router 3 networks. So there we go, our OSPF relationship has come up. As you can see that this neighbor here, we are neighbors with 2.2, we have reached the full state. The neighbor is the BDR, this is our address of our neighbor, and this is the interface that we are forming that relationship out of. So show IP Ospf interfaces, so we can see here that here it is. So we are the DR, which is 6.6, so that's us, and the BDR is 2.2.2. As you guys know, the DR and BDR election, in order to become a BDR, you have to have the highest, firstly it goes off highest priority, so default priority is 1, so it goes off highest priority is the elected as the DR. A priority of 0 means that you don't want to actually partake within a DR or BDR election, so we have a priority of 1 there. and then if the priorities match, then it goes off the highest router ID. So in this case, router 6 has the highest router ID with a 6.6.6.6. So that is why we are the DR, and the 2.2 is the BDR. So there's that, and then we're going to have router 3 here, and we'll go on to our router Ospf 1. I've already done this one, yet, and we want to go the network of 192.168.2.1. So that's our fast Ethernet link, and we're going to put this one in area 2, and then we're going to have our 3.1 in area 2. There's that done, and then we're going to formulate router 4 and router 5. So enable CompT router Ospf 1 router ID. We're going to specify that now of 4, and then we're going to go network 192.168.2.2 area 2. Was it area 1? Sorry. It's area 1. Oh, see, there we go. It's gone down. That relationship's gone down as we had mismatched areas. Wait there. Why did I put this one in? Ah, it went down because I brought it down. We want to be in area 1, sorry, because this guy is in area 2 here. So I want to go onto this guy, and I want to negate these commands, just because of the fact that I want to put these in area 1. So we've got area 1. There we go. I thought they actually come up and went down because they had different app areas, but they won't come up in the first place as they obviously have an area mismatch. So if I go onto here and I go, let's go no again, and I'll put it in area 2 just to make sure, and then I go network and then put it in area 1. That should then come up. Go on to my 5 now, and we'll check if that has come up now. I was just getting confused as to what what areas I've been putting all these in. Router Ospf 1, router ID 5.5.5, and then we'll go network. So this is in area 1 this time, remember that. Then we'll have our wildcard mask, and then we have area, and we're going to put it in area 1. So we should have formal relationship with router 3. There we go. So the reason it came up and then went down, originally I thought it was because they're area mismatched, but if they have an area mismatch, they're not going to come up in the first place. Obviously that's why it come up and come down, because I actually just manually brought it down by negating the command on the other router. But if I go show IP Ospf neighbors, and there we go, we can see that 3.3.3 is the DR. I'm not too sure why that's the DR, as it obviously goes against the DR and BDR election. As if you guys have a look at the show IP Ospf interface. So on this guy we are using interface GI1/1. The DR is 3.3.3, BDR is 5.4.5. It could be because the 3.3.3 is already up, so that's why it's the DR, and because there's no preemption, so 5.4.5 isn't going to automatically take over from 3.3.3 once it comes up. So that could be why in that scenario there. But usually you would see 5.4.5 being the DR. So someone would probably put the, if they actually really wanted it to be the DR, they would change the priority on that guy. And then they'd have to bring it up and bring it down due to there being no preemption. So yeah, there's that. And now we're going to advertise our VLANs. So router Ospf 1, and then we'll go network 10.2 area 1, and then we're going to do our 20.2. So these are the two VLANs. There we go. So these are the two VLANs. So we'll actually form a relationship with router 4 now once this is up, because we are connected to each other via a switch. Network 192.168.10.1 area 1, and then .20.1. There we go, and we should see our relationship come up with the other switch there. But just to have a look, all I'm going to do is just have a quick look at firstly, just to test this, we're going to ping from this PC here to router 6, so hopefully we can get onto this guy in order to do a ping test. Doesn't look like he's coming up, so we'll just do it from the other PC. Sometimes they freeze, but we'll go from PC2, as we're obviously advertising PC2's subnet as well. Don't tell me this guy's froze. There we go. So we can do a trace. So first of all, we'll see if router 3 and router 4 have become neighbours. Just show IP OSPF. There we go, they've just become neighbours now. So there we go, become neighbours on both with the VLAN 10 and VLAN 20 interface. As you guys can see, that 5.5.5, which should be, it's been elected as the DR as it has the higher router ID. So 5.5 is the DR and 3.3 is the BDR, which also should be, as router 4 has the highest router ID. So that's why it would get elected to be the DR. So there's that. So show IP route. So let's have a look at our routes. We're not going to go into these routes, we just want to see them. So as you guys can see, these are our inter-area routes, and then these are our intra-area routes. So our IA is our routes from other areas, so our OSPF intra-area or inter-area routes, and then these are our internal routes, so routes within the same area. So as you guys know, 4.0 is within the OSPF area 2, so that's why we have the inter-area route there, as we have to traverse into another area to actually get to that subnet. So we can go onto our PC2 and we can go to a trace to our 192.168.5.1, which is this guy over here, just to confirm we have full connectivity. Spent trace wrong, which is no good. And there we go, we do actually have connectivity there. It doesn't complete the full ping, the full trace, but obviously we can ping it. So what we're doing is we're going to our 20.2. Obviously the virtual IP is 20.254, which is the virtual IP, but this guy is set as the active. So we go up to here, we go to router 5, then we go up to our 3.1, then we go from 3.1 to 1.1, so we traverse a tunnel over to our London route there. So it's not seeing us going through router 1 to router 2, so we're going straight over the tunnel to router 2, and then we're going down from router 2 into 4.2, and then obviously we're ending up at our 5.1 here. So yeah, hope you guys did obviously enjoy the video. Hope it helps you guys with your studies. Hope you can implement OSPF much easier now. Hope you've learned a few things in terms of DR and BDR, reference bandwidth, the cost calculation to get the cost, sort of like forming neighbour relationships. But yeah, I hope you guys did obviously enjoy the video. Comment, like, subscribe, follow me on Twitter with @networka1a, and hopefully we'll have a new lab up. I'm planning that it will be a switching lab. So yeah, hope you guys did enjoy the video, and I will catch you guys in the next one. See you guys later.